Okay, let's begin. Hello to YouTube also. Today we are going to speak about another paper. It's actually called yet another rope embeddings. So this is actually one of the many papers designed to extend context windows. Okay? Because recently LLMs changed everything, and besides making bigger models, everyone is also concerned about extending the context window for a number of reasons. And it seems like the state of the art right now is the rope embedding, rope positional encodings, and I'm going to quickly introduce that also because we haven't covered rope here. And then this paper is an extension from rope, basically covering some of the shortcomings. Okay. Any comments before I continue? Okay. So the idea is that we are going to create an interpolation extrapolation system to extend the context window. Okay. And they show that this, I really like this idea, putting your main performance diagram right below the abstract. Right. This is really the abstract of the paper. We can start from this, and then we can go into more technical details. So, context window is the size of patches of data that model sees during training, right? And obviously, because you have an attention there, you have to limit the length of the attention span for a number of reasons. First of all, you don't have enough memory, and as we know, attention requires quadratic memory, quadratic in the input size, right? So we are kind of constrained here. So here we have on the x-axis the context window of the model, and on the y-axis we have perplexity. So perplexity is the most common metric when measuring LLM performance. Roughly speaking, this is sort of an inverse from average likelihood of predicting each token given the previous tokens, right? So the way the model works is everything before the current token goes as input, and then we predict, give a likelihood for the next token, right? And then to measure model's performance, we basically do this across the whole length of the context, and for each token, we give everything before that as input, and get the likelihood, and then the likelihood of getting the next token correctly, because at test time we have the correct token, right? And then we basically average that. But because we do this as a negative log likelihood, we end up doing averaging the negative log likelihood and then putting it on the power of 2, so it becomes sort of an harmonic average of likelihoods, right? That's the whole idea. Basically, lower perplexity means better model. Okay. Any comments about perplexity and the context window? Cool. Okay. So the curves here each represent a different model. YaRN is the current presented paper. Others are Code Llama. This one has, I think this one has 32K context. The others are the normal llamas, Llama, right? Llama 2. So they tested with 13B and 7B models. There is this other one, 7B 32K context. Code Llama is actually shorter, but I'll talk about Code Llama later. So there is this other Llama 7B with 32K context. This is a pretty good model, actually. But the YaRNs are the fine-tuned versions from the original model. So they would take Llama to 13B 64K. 64K is the after fine-tuning. The original one has, I think, 16K context window. So they take the original Llama 2, fine-tune it with the YaRN approach. We will talk about this. The idea that we interpolate or extrapolate depending on the situation, the context window. Example, the position embedding. Sorry, we interpolate or extrapolate the position embedding, and then we have larger context sizes. 128K is really large. So the recent announcement from OpenAI said they extended GPT-4 to have 128K context. So that's actually very large, right? That's state of the art. And the others, obviously, we can also always expand the context window, but then performance degrades. Like if you look at these curves, at most models, so this red one is, I think, the 32K model. As soon as we reach the context size, performance degrades rapidly, right? Same with this brown one, this YaRN with 64K, right? This is also degrades after the context window. This is interesting, right? So this brown is the YaRN. They also have the orange, also this the other 64K. Yeah, so the 64Ks degrade very quickly. However, there is the second model, which is fine-tuned twice actually, the 128Ks. These seem to perform better, right? If you look at the pink lines, they don't actually degrade after passing the limit, as compared to Code Llama and the two Code Llamas, right? You can see that they also start degrading around 100K. So Code Llamas, I think, have 100K context windows, but they are also extended, and they're not exactly extrapolations from positional embeddings. They also change the attention a little bit, but we'll talk about this, right? Okay. Comments about the main plots. So the idea is that there have been studies that rope embedding, rope positional encodings, or any other extensions from that still suffer when the context size of the context of text, the prompt length at test time is larger than the context window compared to when it was trained. Right? So if you train models with batches of 32K, and then we try to have a prompt that's 100K, then the model performance actually suffers. As you can see here, like 100K, we reach 100K, and then it starts suffering, right? And now we want a model that doesn't have this problem as much. We'll talk about the limitations of this diagram also, because while we extend to 120K, 128K, but there is no data after that, right? They say because of hardware limitations, we couldn't test for larger than this. So this still doesn't solve the problem of extrapolating beyond the trained context window, but it does extend from the original, I think 8K or 4K to 128K, right? With small fine tuning. So that's a good thing. Okay. Scroll down. Introduction, how amazing LLMs are. I think we spoke about LLMs a lot here, so there is no need to go into details there. I mentioned context window. We need to understand what exactly this means. And perplexity also, I mentioned before. Yes, a little bit. Okay. Now, the theory here is based on this NTK-aware theory. So NTK stands for neural. Oh, let me find it actually. Okay. I forgot what NTK stands for. It's basically a theory
tangent kernel.
Yes,
neural tangent kernel. In that sense.
Thanks. The idea with this NTK theory is that we study how the model learns, how the weights change as we train the model, right? The idea is that we represent the model, the original one, with random weights as as a Gaussian process. But then as the model learns, the weights change, right? And then there is theory describing how this change happens. And then we use these neural tangent kernels. I keep forgetting the name. But the idea is that we learn how the model learns. We study how the model learns, how the weights update over training, over during the training process. And this gives us ideas about why we can't extend the position and encodings beyond the context window, and also suggest how we can fix this. Right. So they cite a few papers that do this called NTK-aware interpolation, and here that we call them dynamic NTK, right? Because we dynamically choose to interpolate or extrapolate or do something in between. Okay. Okay. Any more questions? Okay. Let's talk about ROP embeddings, so rotary position embeddings. So normally, positional embeddings, when you have an LLM, you get tokens from the input, and then they go into these queries and keys, right? Matrices, which are used for the attention, and then if you have many layers, you pass those through the layers. And then at the input, the tokens from the input text, you first tokenize that, and then tokens become the entries for the queue and query and key matrices. However, we also add positional encodings. Because in the position of the token or the word in the text actually matters, right? So we want the model to use that. So the original what's one is paper used fairly simple positional encodings. It was a cosine with a large number there. But since then things changed, and right now the most commonly used approach is this rotary position embeddings, ROP, right? And this is actually very clever, because what we do is we take the vector. So we represent each position with two numbers, right? And then it gives us a complex number. Right? If you look here, we actually have a complex number representing each position. Okay, and this is good because it helps us with the math quite a lot. But this also means that we basically double the size of the embedding vector. But that's fine. What the good thing here is that let me actually introduce these f functions also. So fq and fk are the functions that take the input tokens, so x's are the tokens, and convert them into the q and k query and key vectors. Okay. And now what we do is that and in the attention we have this product, query key product. This is a inner product of two vectors. Okay, and then we do this, and then we normalize, take the softmax, which gives us the attention scores. Right? And then it basically tells how much attention to pay on each token in the sequence. Now, what happens is that because we use these rotary embeddings, we can do we do the conversion from real numbers to complex, blah blah. And then what ends up happening is that this inner product only depends on the distance between the two positions, right? So the inner product happens between each query and key values, okay? And the M and N represent two entries. Now, what happens here is that when we do this change, the attention part for the positions only depends on the distance between M and N. This is good because that's what we want. Without this change, we have a function that also depends on the embedding values themselves, right? But it's a position embedding, and we want it to only represent a position. Okay, so that's the whole intuition idea behind the rotary embeddings.
What is WQ in this equation?
WQ. I don't see W. Ah, you mean this? So these W's, this.
Yep.
So those
Yes.
are the input text. These are before tokenizing, the tokens, but not the embeddings, right? Like the actual text.
Okay.
So where else is it? Is it oh, these W's.
Yeah.
Ah, so those are the matrices. So those are the ways that we learn. So to convert embeddings into query and key vectors, we are first given the linear operators. Right? So those are the operators. Oh, sorry. Okay. So these are the operators that they use to convert from real numbers into complex numbers. Just a notation, really, because we don't end up using them here.
Yeah.
Because you do it twice, right?
How the positions and the original tokens interact with each other.
Yeah. Because if you do this, because so this is the real numbers give us just the position embeddings, one number per position, right? But then you convert it into complex number, and then you need these linear operators to do those conversions back and forth, both ways actually. I don't think we need to worry about this because we end up not using them actually.
Okay, no worries.
Actually, we do use them, but at the beginning to convert into a real number, into a complex number. But doesn't matter too much, I think, for the it's just the operator that converts between real and complex representations of the same number.
No worries.
Okay. Cool. This basically says the function that we use for the queries can be written as a matrix, and this is the W matrix we use for the conversions, right? Because we end up converting into a complex space. Okay. Now, this is all cool, but now how do we actually extend the context window? Right? They call this positional interpolation. Basically, we want to interpolate from a shorter context window that the model was trained on to a longer one. Okay? And here we need to use this notation. So L is the context window size when the model was trained, and L prime is a larger context window beyond the trained limit. Right? You train your model on 4K context, but you want your model to work at inference time to generate a text longer than that. Right? I guess for reference, 100K context would be average sized book. So you may be able to generate a whole book, but this is actually you don't want to generate a book probably, but this is important because if you want to have a chart continuous conversation with your model, you want to keep the previous charts in the context, right? That's how the context length gets so long, usually. Okay. I guess another application is if you want to generate other objects like a graph, the way what MPlan really actually does. That's why we care about longer context windows, because we want to be able to generate large graphs. But that's a bit of a distraction. Back to the paper. So we have these functions that basically scale. So M is this scaling factor, but we basically scale from a smaller context window to a larger one, right? We just do this conversion, and then we have this F function here, which will give us the queries and keys at inference time, right? And then we can run the rest of the model as before. We basically extend the position embeddings to work with longer context. But that doesn't work really well because obviously, as we saw from the graph, model's performance degrades very quickly as you pass the size of the trained context. So to continue, they introduce some more notation. So they call this scale variable S, which is the ratio between L prime and L. We also have this G and the H functions. These are just to generalize the F we had before, right? We had this F, basically G and H show how we scale the size, how we scale the context size, and M is an input also, but basically M and S, right? So before in the previous notation, we had M times L prime over L. Now they want to write a function. Same with H, except we had just a theta. So theta is the other embedding. Let me actually double check to not confuse notations. Oh, that didn't quite work. So these thetas are defined here. So I'm just trying to find the definition for thetas. Oh, here. F with a theta here. Never mind, I can't find what theta is. But oh, it's here. This is used to here. It's just a constant we use to convert from real numbers to complex numbers. And B is this large number, 10,000. And then they also note that this is basically a large number, right? To help with the scaling. And
but it's also relevant, right, for the proximity dependence of the tokens, right? So
yes,
it's very, very large, then it sort of oscillates a lot faster around different sites, and so they're probably not as important anymore.
What do you mean not important anymore?
Well, I'm not sure for that. In line 7, right? So there's the phase.
Line
that
7. What's line 7?
Line 7 or equation 7? Sorry.
Oh, okay, here, yeah.
Yeah. Wouldn't that suggest if theta gets very, very large, then small changes between M and N mean that the whole thing is fluctuating a lot, and so probably averages out to 0?
They do mention the problem later, actually. Yes, the problem happens. And then that's why we have to decide how to interpolate. Because, yes, because the fluctuations can cause problems, yes. Because then you lose the difference between nearby tokens, right?
Yeah.
Yeah. Yes, that happens there too. Cool. Okay, so let's continue. And then we also have we define the wavelength lambda, which is the wavelength of the ROM embedding. This is also motivated by theory. Well, this comes from the NTK theory, because there was a paper showing that actually if you do the correct conversions for your features using Fourier transforms, you will be able to train MLPs performing on par with the CNN on images, for example. So these conversions make an important important change. So that's why they look at how to do how to get the right wavelengths. We'll look at that, I guess, later. Yeah. Comment? Okay. Let's continue. We mentioned the related work. So Llama uses rope embeddings also. And there was another work they mentioned called LM Infinite, which proposes similar ideas. But basically, the main problems with other approaches is that they end up also modifying the attention, which makes it which makes it difficult to adapt to flash attention. So flash attention is more of a hardware solution to speed up the attention calculations. So basically, how do you move things between memory and the processor, and you do clever caching and so on. So when you start changing the attention, these flash attention implementations don't work anymore, right? So they are arguing that these other approaches make all those changes, and we don't. What we do is change only the position encodings, which means we don't have to touch how attention is implemented. Okay? Yes. Cool. Thanks, Arinda. Okay, back to the method. If I talk about interpolations, we actually mentioned this briefly, the loss of high frequency information. So what they observe is that, so if you have high frequencies, I wish they had a diagram here, that would be nice. Basically, what happens is that you end up with a high entropy, no, actually low entropy with big spikes in the attention values, and that's problematic because model ends up not paying attention to the neighbors, right? Because of how this p value can be large, really. So to solve that, what do? You introduce temperature and kind of flatten the distribution, right? That's also what we do for things like calibration. But it's a common technique to kind of control the temperature after softmax. The flatness or the spikiness after softmax, right? Because attention is calculated with a softmax, so you can control that with this temperature parameter, which is actually nice because, again, it can be done without making any major changes. And they also mention it can be done in constant time if you do the math right. This is, again, a similar problem, loss of relative local distances, right? Because, again, this is a similar issue, really. And then it says, if the wavelength is much smaller than the context, then we do not interpolate. They find these solutions really exploring ideas. There is no, I don't think there is strong theory, except that you look at what happens to the model. So if they say if the wavelength is much smaller than the context size, we do not interpolate. Okay. If the wavelength is equal or larger than context size, then we only interpolate, and we don't do any extrapolation. Okay. And then if lambda is smaller than the context size, but not much smaller, just slightly less, then we do both. This is what the NTK-aware interpolations do also. Okay, so they basically do this. They call it dynamic interpolation. So because sometimes you extrapolate beyond the wavelength, but you only do that only if the wavelength is larger than the context, right? Otherwise, there is no need to do that. And then they do a bit of math, but don't worry about this too much. Basically showing that this new updated, because you need to find the new wavelength, right? Then you find the new wavelength from the previous ones. So gamma is a parameter depending on the current values. It's like a scaling parameter. And S is the scale between the new context size and the trained context size. Okay, so this helps us come up with the new G and H functions. Remember the G and H that we used to generate the position embeddings, right? That we use to convert the positions into position embeddings into the queries and keys. Right? So those are those two functions. And then M. So the GM remains just M, but the H before was theta, but now this is this. H becomes the scaled version of theta. Okay? Depending, so you do this dynamically. So when you start generating the beginning of the text, you really don't make a change, right? But then once you start passing the context length, you start updating. you start extrapolating outside the context length. That's the main idea, I think. Good. Okay. They mentioned the dynamic scaling, and they also at the end mentioned that, well, you don't always want to use S as the ratio, because when the context length is still less than the train size, you don't want to do anything. Just keep the scale. Don't keep it 1. Okay. Don't take values less than 1. This also helps the training. Really. Okay. Any comments so far? I've been speaking for a while now. All good? Okay. Again, we come back to this problem of increasing average minimum cosine similarity for long distances. Again, related problem, but now if you have long distances, what happens is that, actually, let me scroll down, is that here, you find out that here, this sentence, because the average minimum distance becomes closer with increasing number of tokens, it skews the attention softmax distribution to spike here, right? I mentioned this before. And then I also mentioned this before, actually. Yeah. Yes, you can use this scaling factor, T, temperature T, and then they experimentally to flatten the curve accordingly. Then they experimentally find value for T given the S, right? So this is found experimentally, basically optimizing for perplexity. That's all. I guess there is one question here. If you do this, do you then report the result on the same data set and then report perplexity numbers? That's a bit strange, because you tune your model for perplexity on the same data as you report for test. I guess you should have a separate set here. I don't think they do, but maybe it doesn't matter too much. Just a question from my side. But this value is found empirically by minimizing perplexity and playing with S. Right? So, but basically they give different values of T, which is the temperature for adjusting the attention values, and then they plot it and they fit it to a curve, and then notice that this sort of curve for T, if depending on S, minimizes perplexity. That's all. Okay. Here they mentioned extrapolation and transfer learning. So the idea is that, well, I mentioned code llama before. This is trained with a 16K context and a scale factor, again found empirically. There is a paper describing this. They show that the network extrapolates to 100K context windows. This is actually good, right? Because you trained on 16K, but you can extrapolate to 100K context window without ever seeing those context values during training. That's a good thing. But this is a different paper. And what they do with this paper, YaRN, yet another rotational encodings. What they do is actually they do 2 steps of fine-tuning on very small data sets. So first they do only like 200 steps for each step of fine-tuning. So first they go from 16K to 64K, and then they go to 128K. Right? We saw 2 model steps. Those are done with 2 iterations. Each iteration is trained for just 200 steps. So step is the number of batch updates, not epochs. This is very few epochs. This is like 10% of an epoch or something. So it's actually very small fine tuning. Right? They argue that this is still very efficient. Okay. Before looking at the more experimental results, any comments? Did I miss anything important? Okay, cool. training. So this is really this is fine tuning. So they took Llama 2's 7B and 13B models and fine tuned those with S16, the scaling 16 and 32. Okay. The training parameters are very standard, and then they fine tune first. Oh, so first they fine tune with 400 steps, and then 200 more steps to get the 128K model. Okay. Bit of evaluations. Let's look at the tables. So this is the context window sizes. So together is the 32K Llama 7B. Code Llama is another Llama, fine-tuned Llama, which is with I think 16K, but it extrapolates very well to long sequences. And YaRN is the model proposed here. So extension method. So together uses positional interpolation. This is only interpolation. So Code Llama uses the NTK-aware extrapolation, and then YaRN is the dynamic thing we mentioned here. And those are the context window sizes. They test on different window sizes, and then the numbers inside are the perplexities. Okay. So notice that how sometimes perplexity gets too large, right? So you can see that the YaRN with the smaller YaRN, the 64K YaRN, jumps out. This is from the curve we saw in the curve, right? Right after it passes approaches the 100K mark, but it can still go just beyond 64K. Maybe it's better if you go back to the plot when we look at this table, because the table is really presented here. So it's this plot is in that table. Okay. Now there are a couple more results. Down here. This is on a different data set, really, but similar results. They also report results for Hugging Face's benchmark. So Hugging Face has this benchmark for open models anyone can use. These are the 4 things they measure. These are designed by Hugging Face, really. And those are not, unlike Perplexity, these are more numbers representing real performances, right? And again, if you look at the YaRN, the 16 one, the 64K one doesn't do so well, actually. But the 32 actually does very well. And here, higher is better, by the way. All those 4, higher is better. Okay. So if you look here, those actually both of them do pretty well. And then there is no much degradation from the original models, unlike Together and Code Llama, which degrade from the original models quite a lot, actually. Right. Those are the benchmarks for the original models. And then it's important that what they say, and it makes sense, that we don't only look at perplexity and context window, but actual tasks. Those are actual tested on actual tasks. And those models actually suffer quite a bit, both Together and Code Llama. On the other hand, YaRN doesn't suffer too much, actually, very little, right, compared to those. So I guess that's reasonable, just to give us an idea that models is still good. And that's all, really. We talk about benchmarks, and yeah, this is all. I'll stop here. Any discussion points about context windows or Rotary embeddings and any of these?
So what is the underlying assumption there that if I zoom out on my token problem, it's on a very large scale sort of behaves similar as on a smaller scale, and we just have to.
Yes, the idea. What do you mean assumption? Is it assumption or the result or goal?
I mean, why does it work, right?
Why does it work? Basically, And the extrapolation actually happens only with positioning embeddings. That's the thing, right? The model, the attention still doesn't pay attention to text, to the embeddings before the context, right? So if you have a, let's say, 16K context window, and you give a context which is 100K.
Mm-hmm.
So what happens here is that we only pay attention to the position of embeddings, right? Before the 16K, we only look at the position of embeddings,
Yep.
And not the actual embeddings, which I think is interesting, and that still helps the model quite a bit. I think that's what we want. That's what we do, and it works because we use this sinusoidal or cosine function in the wavelengths really in a clever way to allow extrapolation, and we don't extrapolate if we don't have to, right?
Yeah, but
The
it's
extrapolation inside can help actually.
yeah, but when we do this extrapolation, as far as I understand it, we do sort of pretend the bigger context is actually a smaller context, but we sort of fill in the gaps.
Oh yeah, that's actually a good point. Yeah, because of the Fourier transforms, right?
Mhm.
It's like so I didn't mention this actually, yes, but it is part of the theory that because we have such a large context window, and then we want to represent it as just one number, right? And it's difficult. But however, if you do the Fourier transform and look at the wave level, at the waves really, we give more information to the model, better information. That's the feature transformation that helps.
Mhm.
I think that was the main point.
Yeah. Yeah, I have to read the paper and try to go to the math. It's very hard to follow exactly what's going on.
Yeah, I tried to skip the math a little bit because I guess this is the important part with the conversion to complex numbers, which is what Rob does really. The rest, scaling, they do the math mostly to motivate why scaling, only scaling without any dynamic checks can be hurtful for the model.
I mean, the complex
yeah.
numbers are really just to get the positional dependence in, right? It's
Exactly.
we don't have complex numbers at some point anymore, right? Because they
exactly. You can't be you do you basically double the size of position embeddings. You use two numbers and then assume they are the real and imaginary parts of the complex number.
Yeah.
And then you end up losing the embedding itself and just the distance. You keep the distance. That's because when you multiply, when you do an inner product with the complex vectors, the things just cancel out.
Yep.
There's the motivation there. I think that part is clearer, but the rest is not so explicit. Like they've shown the math and the numbers, but it's hard to follow. I think it's more like motivation. Like, okay, we do this is the math, and then we do this experiment to find the right number, the right values.
But it's like sort of some.
Yeah.
I think the scaling dependencies are quite interesting, right? Because stuff like this happens quite often in physics. I think, for example, where you have like systems behave similarly-ish at different levels, and usually this behavior is sort of described by these exponents. So I have to dig deeper.
Well, you get exponent because of complex numbers. Right? It's just that it's because you have a complex number, you end up with an exponent. Is it what you mean, or you mean?
Yeah, I mean the exponent sort of here would give you some sort of scaling behavior, right?
You mean this exponent, or you mean the power?
Yeah.
Yeah. Right. Yeah. I see. Yeah. So you can look for you can look further from the current position.
Yeah. What was small d in this equation again?
Let me find it. one of the dimensions. I can't remember. So theta d, if you go back. This is the big D. So big D is the dimension of embeddings, right? Small d, define that.
The actual embeddings of the tokens.
Yeah. Yes.
Yep.
Theta d. They don't actually define d. We only have theta d, right? Well, what is small d? Let's try something. Dimension d. Rope embedding of dimension d. What? There's a dimension of what though? Oh, dimension d. I'm not sure dimension of what. Right?
Yeah.
This is dimension of embedding the dimension. I guess there's the dimension. So what we do here is that we change the base for oh, it's not related. No. This is the because the dimension of rope embedding is just 2, right? That's what I don't understand. What's the
Or could that be the context length, right? Which is also like 8-dimension of sorts.
Maybe it says that the rope embedding a dimension d.
Because it was like spanned by a base of the complex numbers, right? I think I'm not. I have to read it, but I'm sure that there's some really neat geometrical idea behind all of this.
Yeah. So those are taken from different papers.
Yeah.
So that's why maybe they don't introduce the details here because they are taken from different papers. Yeah. Okay. Any other comments? I'll stop recording.